Imagine you're handed a real-world problem. Optimize wireless network scheduling to maximize throughput under resource constraints. You know reinforcement learning could solve it, but where do you even begin? You need to translate that vague description into a precise mathematical model. Define states, actions, rewards. Then write an executable environment. Train a policy. And if the goal changes, say, from maximizing performance to minimizing energy, you'd repeat the entire process. This is the painful reality of deploying reinforcement learning in real-world domains. Robotics, supply chains, network management, industrial automation. The gap between a natural language idea and a deployable policy is wide, and human experts are stuck bridging it, one manual step at a time. But what if we could automate this entire pipeline? Not just generate code, but reason through the task, formalize the decision process, and produce a correct, reliable policy, all from a single free-form description. Today, we dive into ALAMP, a novel agentic LLM-based framework that does exactly that. It's not just another automation tool. It's a structured, verifiable, multi-agent system that transforms natural language into a complete reinforcement learning workflow, end-to-end, with transparency, reliability, and remarkable performance. Let's break it down. Reinforcement learning works best when you have a well-defined Markov decision process, or MDP. That's the formal bridge between your task and your agent. It specifies what to optimize, how actions affect outcomes, and what the reward signal should be. But in practice, turning a real-world problem into an MDP is fragile. It's error-prone. A single misinterpreted constraint, a poorly defined reward function, or a mismatched state space can derail training, no matter how advanced your algorithm. And here's the kicker. This process is manual, expert-intensive, and not reusable. Change the objective. Rebuild everything. Swap from maximizing throughput to minimizing latency. Start from scratch. Even minor tweaks require full re-engineering. That's not scalable. That's a bottleneck. ALAMP solves this by automating the entire pipeline, from natural language to trained policy, using a modular multi-agent LLM architecture. Think of it as a team of specialized AI experts, each responsible for a specific stage of the workflow. Here's how it works. When a human expert first sees a task, they don't jump straight into math. They understand. They ask, what are we trying to achieve? What can we control? What are the hard limits? ALAMP mirrors this process with 4 specialized agents. Parameter agent identifies fixed values like bandwidth, noise density, or number of users. Objective agent extracts the goal, e.g. maximize network throughput, and frames it in context. Variable agent distinguishes between decision variables, what the agent controls, and system variables, what evolves in the environment. Constraint agent captures feasibility rules like only one user can transmit per time slot. Each agent outputs a clear, human-readable, structured JSON, not just text, but formalized knowledge. This ensures transparency and allows experts to inspect, validate, and refine any stage. Now with the components in hand, ALAMP moves to the formulation phase. The modeling agent takes the objective and constraints and translates them into a formal MDP structure. \max \pi math b \pi lift. It ensures the objective is mathematically sound and that all constraints are explicitly encoded. The SAR agent, state action reward, then defines the core components of the RL environment. State, a vector of channel gains, user positions, or inventory levels. Action, discrete choices, like selecting which user to schedule. Reward, a function tied directly to the objective, e.g. Shannon capacity in wireless networks. Crucially, this is not a black box. Every component is traceable. Every decision is justified. And to prevent errors, ALAMP includes an error correction module. Each agent assigns itself a self-confidence score. If it's unsure, it re-examines its output, reducing hallucinations and ensuring semantic alignment. Now the final leap, from formal MDP to executable code. 2 agents collaborate here. The environment agent defines the transition dynamics. How does the state evolve? It encodes physics, like path loss, fading, or Poisson demand, into the environment logic. The coding agent generates full PyTorch-based code, a custom gym-style environment, a queue network, a training loop with replay buffer and target updates. All code is clean, consistent, and follows best practices. And if there's a syntax or runtime error, a feedback loop kicks in. The agent rewrites, the executor tests, and the process repeats until the code runs. No more debugging hours. No more it works on my machine chaos. To test ALAMP, we ran experiments across 5 diverse tasks. Classic control, cart pole mountain car. Domain-specific, wireless scheduling, drone delivery, inventory management. We measured 3 success rates. Modeling success, were states, actions, and rewards logically correct? Coding success, did the code run without syntax errors? Policy generation success, did the trained policy converge and meet the objective? Here's what we found. Task ALAMP Lite ALAMP Gemma 327B, GPT-4o single. Cart pole 1/0.95/0.95, 1/0.6/0.35, 1/0.75/0.45. Wireless 1/1/0.45, 0.95/0.6/0.15, 0.8/0.9/0.2. Drone delivery 0.8/0.95/0.45, 0.55/0.5/0.15, 0.35/0.55/0.1. Inventory 1/0.55/0.3, 0.85/0.25/0.0, 0.65/0.05/0.05. The results are striking. A lamp consistently outperforms single-model baselines, especially in complex custom environments. Even its lightweight version, built on Gemma 327B, beats the much larger GPT-4o in policy generation success. How? Because decomposition beats scale. Let's dig deeper. Why does A-Lamp succeed where single models fail? We analyzed 460 trials. The key insight: failure modes reveal the real advantage. Consider a single LLM. It might generate syntactically correct code, but semantically disconnected from the task. For example, a policy that schedules users randomly, even when the goal is to maximize throughput. A lamp eliminates this spurious coding success. In wireless and drone tasks, such failures drop by 37.5% or more. It also reduces complete failures, where both modeling and coding fail. In drone delivery, that dropped by 60%. In inventory, it was eliminated entirely. And even in classic tasks like cart pole, A-Lamp turned 91% of previously failed training runs into success by stabilizing the training dynamics. So the gains aren't just in output, they're in robustness, reliability, and resilience to error. Yes, and here's the proof. In the wireless scheduling task, the optimal policy is greedy. Always schedule the user with the highest instantaneous rate. That's mathematically provable. We trained a DQN policy using A-Lamp's generated environment. The result? The training curve rose quickly and stabilized. The final policy's performance closely matched the greedy baseline, which is optimal. This isn't just working, it's correct. The generated policy preserves the task's optimality. We confirmed this across all tasks. A lamp doesn't just generate any policy, it generates one that solves the problem as intended. A lamp is more than a tool. It's a paradigm shift. It lowers the barrier to entry for RL. No need to be a mathematician, a coder, or an RL expert. It enables rapid iteration. Change the goal. Just update the description. A-Lamp regenerates the entire pipeline. It ensures correctness through verifiable stages, not black box magic. It scales to complex domains, not just simple gym tasks, but real-world optimization problems. And perhaps most importantly, it proves that structured, modular agentic reasoning is the key to reliable AI automation. We're not done. Future work includes finer-grained coding agents, e.g., dedicated modules for environment construction, hyperparameter tuning, integration of domain-specific priors and knowledge graphs, adaptive validation and self-correcting loops. The goal? To make RL not just possible, but predictable, reusable, and trustworthy. Reinforcement learning has enormous potential, but its adoption has been held back by a bottleneck, the gap between idea and implementation. A lamp closes that gap. It turns natural language into formal models, executable code, and high-performing policies, automatically, reliably, and transparently. This isn't the future. It's here. And if you're working on real-world decision-making problems, whether in networks, logistics, or automation, this is the tool you've been waiting for. Because the next time someone says, let's optimize this, you won't need to start from scratch. You just need to describe it. And A-Lamp will do the rest.